Hi everyone, my name is Jain and today I'll be discussing our work to learn to design accurate deep learning accelerators with inaccurate multipliers. This is joint work with Gonzalez and Stoica from UC Berkeley and Safeen Huda, Maas, and Azalia Mirhoseini from Google. Deep learning has a very distinct and rising inference energy problem. In recent years, the rise of high-parameter models such as ResNet and BERT has led to increasing total computational demands from inference. Here we show the number of floating point operations required for a single inference forward pass for an emerging model. In addition to this, inference already is the dominant workload for deep learning in data centers today. Both AWS and Facebook report that inference is over 80% of their data center deep learning workloads. So the net consequence of this is that the energy demands of inference are rapidly climbing. To hopefully solve this, we can explore a few different methods of optimizing the power usage of deep learning accelerators. This includes quantization and pruning. The reason that these methods are interesting is that deep learning methods are fairly tolerant to approximations. However, in this work, we focus on approximate multiply and accumulate units. These are emerging multipliers and adders that trade off accuracy for power. Now we know that this is a complementary approach to methods such as quantization and sparsity. But the key challenge is how do we maintain high accuracy under approximation when utilizing these methods? Our research question, therefore, is how to achieve power savings with an approximate inference accelerator without any accuracy loss on a large-scale dataset. This goal hopefully will help enable the deployment of approximate multipliers in production chips on today's workloads and without any loss of accuracy for end workloads. Now, as background, we examine approximate multiply and accumulate units to trade off power and accuracy. For these components, parts of fully accurate circuits can be removed to trade off accuracy for better power efficiency. So let's take an example here. We can take an adder and we can truncate the carry chain in the adder. And so here we have a 4-bit full adder, and we can truncate, in this case, the second carry bit. And by truncating this, we reduce total power requirements when evaluating this circuit. But it comes at the small cost of accuracy. For inputs that exercise that particular carry chain, we now note that we will have reduced accuracy. Now, there has been extensive prior work to produce such multipliers and adders, and we have a few citations here. And these cover a very broad spectrum of different design techniques. But I want to note that in this work, we only consider functionally approximate circuits only. So these are circuits that are entirely deterministic, whose behavior we can model very accurately, essentially. And so we're not considering things like analog computing or different methods that may be noisier or harder to kind of emulate ahead of time. And so here's an example for an approximate multiplier. We have this from, actually, this is a multiplier that's proposed at date in 2017, where we have multiplication of A times B, both 8-bit values, yielding an approximate C. Overall, this multiplier has a 4.2% mean relative error, but results in 3.6x lower energy consumption when we consider the multiply accumulate unit in isolation. Now, I want to note that what's very interesting here is this multiplier has error that is depends heavily on the input values that we consider. And so if we look at multiplicand and multiplier values here, values that are close to 0 have significantly higher errors, but the error also is fairly sparse. So there are periodic values here. When we examine the multiplication for these values, that incur errors up to 70%. And so these high errors need to be tailored effectively to the workload to ensure that these occur in areas where the workload can tolerate error. And so one of the challenges here, when we consider approximate multiply accumulate units in the context of deep learning, is that prior approaches degrade accuracy for end-to-end workloads. So here we consider a variety of different prior baselines here. We note that they're tested on data sets that are relatively small also, such as CFAR10, CFAR100, or this Caltech data set, for example. And what's important to note here is that none of these methods is able to achieve a zero loss result. So you must incur an accuracy penalty. And so now this is a trade-off for applications to consider, that to yield potential power savings, they must sacrifice some accuracy in their workload. In our work, we show it's in fact possible to use approximation and maintain high accuracy. This is a very interesting result, and we show that on a large-scale data set with a large model, in this case ResNet 50, it is possible to maintain zero loss approximation. We also evaluate on 3 orders of magnitude more data than prior baselines. And so this result hopefully is a clear indication of what approximation can yield in real-world production workloads. The key insight in our work is to add additional approximate units next to an exact unit as a low-power fast path. So here in this diagram, as we begin to evaluate the neural network layer by layer, we take the results of the prior layer from the activation buffer, and we have a learned per layer router that dynamically routes that layer's activation to one of several approximate matrix multipliers. And these multipliers live in a multi-tile matrix multiply unit. And so here we can have an optional exact unit as a fallback, here with 0% error at 100% power. But we also have several approximate units, in this case with 2% error and 70% power, and 10% error and 10% power. So the advantages of this is that for error-tolerant workloads, in this case particular layers of a deep neural network, we can save power by using the approximate matrix multiply unit of choice. But for sensitive workloads that do not tolerate approximation well, we can maintain accuracy by using the exact multiply accumulate unit. We present AutoApprox, a full-stack framework to design zero-loss approximate accelerators. Our contributions are as follows. First, we propose a novel approximate architectural template for deep learning inference accelerators based on the TPU v3. This design provides exact fallback for legacy or workloads that are error sensitive while enabling error-tolerant workloads to take advantage of power savings via approximation. Second, we will discuss how we utilize whole chip power, performance, and area estimates in order to compute our objective function to determine the optimal chip design for a particular workload. We demonstrate that it's important to utilize whole chip estimates here because multiplier-only estimates are poorly correlated with whole chip results post-synthesis. Third, we demonstrate a new method for fast end-to-end accuracy simulation of the chips, where we take a deep neural network workload and run it on a target data set on a particular candidate hardware design to determine the accuracy impact of approximation. Now, this is not typically feasible due to the expense and difficulty of circuit simulation, but we demonstrate that it's possible to accelerate simulation by up to 7,000x via caching and matrix factorization. And lastly, we'll discuss our approach for ML-guided search to quickly explore a very large combinatorial space of these circuit designs by leveraging a novel Bayesian optimizer. So first, I'll discuss candidate hardware generation. Here we want to automatically generate diverse approximate accelerators. We consider a TPU v3 based architectural template. In this case, this is a floor plan of the TPU v2 that was published a few years ago. And here, AutoApprox will instantiate anywhere from 1 to 4 additional systolic arrays. And these are each approximate systolic arrays that are placed alongside the existing exact matrix multiply unit in the TPU. And so these sister approximate matrix multipliers are then going to be selected at runtime on a per layer basis. Now, in our work, we consider a bank of 36 multiply accumulate units from prior work. And this can be augmented with new designs as new designs come out. The advantages of this approach are threefold. First, we retain fallback to the exact matrix multiply unit for non-approximate workloads. Second, this remains simple to deploy via one additional compiler pass. And lastly, this is more efficient than routing to multiple multiply accumulate units inside a single matrix multiply unit. The reason for this is actually because by utilizing separate systolic arrays, we can further reduce interconnect power consumption. Now I'll discuss whole chip power, performance, and area estimates. So when we begin to examine measuring power and area for a particular candidate design, we note that that the energy consumption on a multiplier-only basis is poorly correlated with whole chip energy consumption. So here on the x-axis, we show the energy consumption for a particular approximate multiplier in isolation. And on the y-axis, we show the relative power consumption for the systolic array as a whole. And it's important to note here that these are somewhat correlated, but fairly weakly correlated. So it's not good enough for actually determining what the expected energy consumption of the chip will be post-synthesis. So why is this? Well, one reason is that a smaller multiplier, which may actually be a multiplier that consumes more energy than another approximate multiplier at equivalent error, will consume lower power overall in a total design due to less interconnect power consumption from having to use shorter wires. So this is one reason why lower per multiplier energy consumption does not necessarily mean that the chip itself will consume less power. We now discuss how we perform fast end-to-end accuracy simulation. We want to consider in our work what the impact of approximation is on very large data sets, but this is cost prohibitive to simulate. We consider ImageNet in our work, which has 1.2 million training samples and 50,000 validation samples that we actually then evaluate the model against to determine validation accuracy. These images are also very large relative to prior models, and so ImageNet models will typically consume images at a resolution of 224 by 224. Now, I want to note that MNIST and CIFAR10 are not representative of production workloads in practice. The reason for this is that both MNIST and CIFAR10 are relatively small data sets that are well separated. So approximations here are very unlikely to cross the decision boundary. However, in ImageNet, this is very common, for example, where there's many different breeds of animals such as dogs or cats, and many different similar overlapping categories such as cars, automobiles, and race cars. So evaluating a single ImageNet sample with a commercial simulator, we note, takes 4.2 hours. So this is cost prohibitive. We have 50,000 validation samples to score, and so this would take far too long to evaluate. As a solution here, we cache results when we perform circuit simulation on a per multiplier basis and use this to estimate accuracy very efficiently. And we note that this kind of operation can be GPU accelerated as well to utilize parallelism to further accelerate simulation time. This is similar to prior work by Mrazek et al., but we note that this approach does not scale to high bit widths. And so as you start to approach bit widths past 8-bit, we note that this approach rapidly consumes large amounts of memory. And so we know that we can factorize these lookup tables to efficiently compress them and store them within GPU memory, which enables us to achieve high speedups at low cost. Lastly, I'll discuss ML-guided search. So we utilize a novel Bayesian optimizer for searching the large combinatorial space of circuits. I will now discuss our ML-guided search procedure to jointly search for hardware designs and the mapping of workloads to that hardware design. The first phase is determining which approximate matrix multiply units to use. And so here there's a power, accuracy, and area trade-off. As we add more approximate matrix multiply units, we can achieve higher accuracies and lower powers by better tailoring the chip to the individual approximation sensitivities of each layer of the neural network. But this comes at an area penalty. The second phase of the search procedure is determining how do we map each workload to each tile. Different layers in neural networks have different variable tolerances to approximation. So we have to leverage this by routing certain layers, such as the first layers or the last layers, to less approximate tiles in this case, while their other layers can often tolerate more approximation and save some power. And so determining how we map workloads to each tile is an important but complex stage of the search process. So since the search space is so large, we have to be efficient in how we search this. And so we utilize ML-guided search via Bayesian optimization. So in Bayesian optimization, we learn a surrogate function that allows us to more efficiently traverse a complex space. Now, I'm not going to go into too much detail in this section of the talk because the derivation and formulation for how we approach this is all in our paper. But at a high level, this is our optimization problem that we can formulate describing the task at hand here, where we wish to minimize total energy consumption subject to an accuracy constraint and an area constraint. So to make the search process more efficient, again, I talked about using Bayesian optimization. This balances exploration with exploitation to discover efficient designs. A learned surrogate cost function is then used to make search trials more efficient. So Bayesian optimization improves the sample efficiency of the search process, but we note that there are many catastrophic regions in the search space. If we approximate a particular layer here in a neural network workload, it may result in very poor accuracies that we cannot recover from. And so we can explicitly prune these very catastrophic trials out by using a greedy lower bound. And finally, we relax the combinatorial search space into a continuous one. And so this has a tremendous impact on the search efficiency of the process by making it more efficient to search and allowing Bayesian optimization to more efficiently traverse the search space. Now, I'll discuss all these details in the paper itself with detailed formulation again, but this hopefully gives some ideas about how we improve the search efficiency of AutoApprox. So in the first row, we have the exact 8-bit matrix multiply unit. We report total chip energy and total chip area relative to the exact matrix multiply unit. And so in this case, it's 1.0. When we report chip area here, this area includes the exact matrix multiply unit. So this exact chip achieves a 72.1 top 1 accuracy on ImageNet and 90.7 top 5 accuracy. If we utilize two relatively competitive baselines for designing these approximate chips, we find is that accuracy drops to be 1 to 6% lower accuracy than the baseline. So while they do save some total chip energy, they're unable to achieve a zero loss result. We demonstrate using the AutoApprox design framework. We can yield two novel designs here, a power optimized and a balanced design here, which has, in this case, 3.2% to 6.1% total energy savings. I also want to note, AutoApprox Large is able to achieve comparable accuracy to the baseline here, the exact matrix multiply unit, with less chip area. How could this be? Well, in this case, AutoApprox L only utilizes approximate matrix multipliers. There is no exact matrix multiplier. So in fact, it was not necessary to achieve full accuracy. We now compare AutoApprox to different baselines, and we find that it in fact is Pareto optimal to these baselines. So again, this is ResNet 50 on ImageNet. And compared to discrete Bayesian optimization, as well as a single layer grid search in this case, AutoApprox finds significantly higher accuracy results at lower overall power consumption. We also evaluate VGG19 on CFAR10. VGG19 is a relatively high parameter, large model for image classification again, but in this case, AutoApprox is able to outperform baselines. So today we discussed learning to design accurate deep learning accelerators with inaccurate multipliers. The problem we were trying to solve was trying to discover How to achieve power savings with an approximate inference accelerator without any accuracy loss on a large-scale data set. The approach we took on our work was to pack heterogeneous approximate matrix multiply units as sidekicks to a fallback exact matrix multiply unit. So at runtime, we route each component of a workload, such as a layer of a deep neural network, to one of the many approximate matrix multiply units on the chip. This allows tailoring approximation to the workload so that error-tolerant components of the workload save power. The contributions of our work are fourfold. First, we propose a new architectural template for a TPU v3 inspired design with approximate matrix multiply units while preserving exact fallback. Second, we utilize whole chip power, performance, and area estimates. And these are higher quality estimates that correlate better with in the wild results from synthesized chip designs. Third, we propose a new fast end-to-end accuracy simulation that allows us to evaluate relatively quickly what is the end-to-end accuracy of an approximate accelerator for high-level workloads on large-scale data sets. And lastly, we propose a novel ML-guided search mechanism based on Bayesian optimization to efficiently search the large combinatorial space of chip designs. The key results from our work are that first, AutoProc saves up to 6% of total MXU power for an end-to-end evaluation benchmark on a real TPU-inspired design at under 10 nanometers. Moreover, this method significantly outperforms competitive baselines. Finally, this work opens up new orthogonal avenues for chip efficiency via proximate computing beyond quantization and sparsity, which is deployed on chips today. If you're interested in this work and want to learn more, please read our paper, but also do not hesitate to reach out to me at parsj@berkeley.edu. Thank you very much.